Hello and welcome learners of Dr. B.R. Ambedkar Open University. Today we are going to concentrate on regression analysis. This is being offered for the MBA students of Health, Care Management and Hospitality, basically HHCM, which is nothing but for the first year, first semester students, block 2nd, correlation and regression, and the unit is unit 6, regression analysis. So what comes to your mind when you think of regression analysis? Imagine that a doctor is looking for lots of patients, and these patients are having a lot of issues with their blood pressure. So is there a relationship between patient's age and then the high blood pressure? And what about the strong relationship between the two? And what about the predictability of these patients? Actually, a patient's blood basically going to tell you a lot about their weight as well. So on that note, let us look at more deeply into regression analysis. Regression analysis, as we all know, is a predictive tool. It's not just a mathematical or a statistical concept, it goes beyond that. And it actually taps into the clinical intuition of the practice. There are quite a few stages for it. In the example that I gave you, the dependent variable is nothing but blood pressure. And what about the independent variable? Yes, you're right. It is the weight. And the goal is to build a line that best fits into the data that makes the prediction. And we will try to show you through the visuals in the subsequent slides. Let's dive deep into what is regression. Regression, as we know, that it's a relationship between the y, that is the outcome variable, and x, which is the predictive variable. And it also helps us to estimate and predict the y for the given x values. For example, predict the blood pressure from age. That's what it is. So where do doctors and hospital administrators use regression? There are plenty of uses. Few of them, if you look at it, is basically to risk the prediction like diabetes, heart diseases, ICU mortality rates, all of them. And then the operational part of it, if you look at it, the length of the stay, the readmission of the risk, all of that. And in the research also, the institutions like hospitals and hospital administrators use it, like the dose and the response, treatment effect, all of that. So there is always this confusion between regression and correlation. In the previous classes also, we tried to demystify the difference between the two. Correlation measures the association. There is no relationship of prediction there. But whereas regression tries to fit the equation like y equals to f function of, or you can call it y equals to function of x for prediction. That's very simple, isn't it? Like you have pack of ears predicting FEV1. Let us look at some of the key terms. What are the key terms in the regression analysis? Few of the key terms that you have to keep in mind. First and the foremost thing is the dependent variable. Here in this case, dependent variable is the outcome variable as well, like blood pressure, and which is also represented by y. Usually dependent variable is written with Y capital letter. Then look at the independent variable. In this case, the independent variable, which is nothing but the predictor, for example, age, and there can be multiple predictors like the body mass index as well. And then the coefficient, which is nothing but the effect of size on each of x and y. As we are going ahead, we will try and unpack you this whole simple linear regression. Simple linear regression because there are lots of managerial decisions at hospital, at a company and at a firm that people have to make. So regression analysis is basically used to develop an equation showing how the variables are interrelated to each other. And the variable being predicted is called the dependent variable and is denoted by y. And then the variables that are being used to predict the value of the dependent variable can be called the independent variable, denoted by the letter x. As we move along, we will try and look into it. So one predictor x explains the continuous outcome of y. Look at the equation. The equation, does it ring the bell in your head? Yes, you are right. So look at this equation. Y equals to a plus bx plus e. And here a is nothing but intercept, b is nothing but slope, and when you say slope, which is any change in y per unit of x, will be reflected in the slope. And now look at the simple linear regression model, and it can easily be represented through the model, and this time we are presenting you the population model. Look at the figure. In this figure you see yi equals to beta naught plus beta 1 xi plus the error term, and each one of them is represented like what is yi? Yi is nothing but dependent variable. What about the beta naught? The beta naught is the population y-intercept plus, and what is beta 1 here? Beta 1 is population slope coefficient, and then xi is nothing but your independent variable, and the e is here the random error term. So that is the line of the equation which is called the simple linear regression model. We can even go further and try to look at it through the other example. If you look at the red line, that you can clearly see that the observed value and the predicted value and the error terms are represented on that straight line. So you can see the random error for this x value, as well as the slope is given as beta 1. This is a graphical representation of the same equation that we have seen some time back. There are few assumptions that you have to keep in mind as far as linear regression is concerned. The first and the foremost assumption is the normality. Y values are normally distributed for each value of x. Similarly, the probability distribution of error is also normal. The first assumption is the normality. Do keep that in mind. The next one is the homoscedasticity, which is nothing but the constant variance. The third assumption is the independence of error term often equals to 0. That's why you have to look at the independence of error term. And then linearity. Most of the regression is linear in nature. And the last and the final one, the variables are measured without error, which is also called as non-stochastic. So these are the few assumptions that you have to keep in mind as we move along. Then the simple linear regression model, you can see it where y equals to beta naught plus beta 1 x plus the error term. And here beta naught and beta 1 are the parameters of the model. And then the e is the random variable, which is the error term. So these kind of terminologies and jargons that if you keep learning, you will be able to understand it more easily. Let us move on and look into the relationship between the two variables, which is the always approximate by a straight line, and regression analysis involving two or more independent variables is called multiple regression. We will also try and solve a problem so that you understand it clearly. So what is the formula for A and B? Look at first the B part. B equals to sigma into xi minus x bar into yi minus y bar, which is divided by sigma into xi minus x bar whole square. Are you going to remember this formula? I'm sure you will. So let us look at for A. Here A equals to y bar minus b x bar, which is nothing but the fit line minimizes the squared residuals. Here is the symbolic and also visual representation of age and systolic BP. You can clearly make out how the dotted lines in the graph are able to give you that straight line visuals. Let us now pay attention to the residuals and the errors. The residual is nothing but observed minus predicted. What you have observed and what you have predicted, that's the difference, and this difference is captured through residual. The other one is looking at the patterns. Checking the pattern should be random around 0, and non-random residuals will have the model issues, and that is the reason. So let us look at the estimated linear regression Let us look at the estimated simple linear regression equation, and it is represented through the estimated linear regression equation, which is nothing but y hat equals to beta naught plus beta 1 x. Very simple. And here the graph is called the estimated regression line, and beta naught is the y-intercept of the line, whereas beta 1 is the slope of the line, and y hat is the estimated value of y for given x value. So I'm sure that you will not get confused with y and y hat, and that is the reason we will have the estimation process. This estimation process will give you lots of hands-on experience. And now let us look at the simple linear equation we have been talking about. So what is the simple linear regression equation for the estimated values? Y hat I equals to beta naught plus beta 1 xi. Here y hat is nothing but the estimated or y value for observation I. And what is beta naught? Estimation of the regression intercept, and then beta 1 is the estimation of the regression slope, and xi is the value for x observations I. Is that clear to you? I'm sure that it's clear to all of you. Let us look at, there is a method called least squares method. The least square method runs on the least square criterion, which is nothing but minimum and sigma into yi minus y hat I whole square, where yi is nothing but observed value of the dependent variable for the observations, whereas y hat I is the estimated value of the dependent variable for the ith observation. We can also look at the slope for the estimated regression equation, which is written as beta 1 equals to sigma xi minus x bar into y minus y bar divided by sigma into xi minus x bar whole square, where the values are represented as xi, value of the independent variable for the ith observation, yi is the value of the dependent variable for the ith observation, and then we have x bar, the mean value for independent variable, and y bar is the mean value for the dependent variable. Too many equations and too many jargons, but if you start calculating, things will become much easier. So don't get confused, dear students. It will be much fun if you look at the solved problem, and we are going to do that. So let us look at the other formula, that is for the beta naught. So beta naught equals to y bar minus beta 1 x bar. And let us look at this very important example, and I want you to look at the problem. In this problem, there is a company called Reed Auto which has periodically been collecting special week-long sale, and as part of the advertisement campaign, Reed runs one or more television commercials. So what happens during the weekend? There will be some proceedings of the sales. So the data from the sample of 5 previous sales are shown on the next slide. Let us look at this one. I want you to consume this data. Look at the number of TV ads, which is represented by X. You know what is X? That is the independent variable. You're right. And what about the number of cars sold? That is represented by Y. And you're right. That is nothing but your dependent variable. So number of ads shown versus the number of cars sold. Is there a relationship? Yes, indeed. So you can calculate the sigma x and sigma y. So you will sum them up and then you get the mean. X bar is nothing but the mean of the x values, and the y bar is nothing but the mean of the y. So y bar equals to 20 and x bar equals to 2. Now you start computing this in this formula. This formula we have been telling you about. Look at the formula. If you insert that, let's first find out beta 1. Beta 1 equals to sigma xi minus x bar into yi minus y bar and divided by sigma xi minus x bar whole square. If you start inserting the data, you will get 20 by 4, which is nothing but 5. So your beta 1 value is 5. Now look at the other one. So y-intercept also you are going to find out, and then beta naught equals to y bar minus beta 1 x bar, which is nothing but, since you got the value of beta 1, you can insert that in this equation. So you will get 20 minus 5 into 2, which is nothing but 10. And what about the estimated regression equation? You're right. Y hat equals to beta naught plus beta 1 xi. Here, start inserting the values of beta 1 and beta naught. So y hat equals to 10 plus 5x. Isn't that simple? This can also be represented on the line. Look at the graph. It's quite evident that beta values are inserted. So y hat equals to 5x plus 10. That's what we got it from this diagram. Now let us try to compute the coefficient of determination. So the relationship among SST, SSR and SSC, quite a good abbreviation or acronyms, but you will learn it. Let's unpack for you. What is SST and what is SSR plus SSC? So SST is nothing but total sum of squares, and SSR is nothing but sum of squares due to regression. And what is SSC? SSC is nothing but the sum of squares due to error, and for each one of them we have a formula. Like for SST, sigma into yi minus y bar whole square equals to SSR is nothing but sigma y hat I minus y bar whole square plus SSE's formula is sigma yi minus y bar whole square. That's how you will be able to get it. So the coefficient of determination is R square equals to SSR divided by SST. You know what is SSR and SST. I'm sure that you have learned it. And if you start computing and start putting your equation ideas here, then you will get R square as 0.8772. which is a great regression equation. So the regression relationship is very strong. So 87.72% of the variability in the number of cars sold can be explained by linear relationship between the number of TV ads and the number of cars sold. Do you see the relationship now? Every time that you come across a TV ad, there are few cars being sold, and that's the beauty of regression analysis. I hope that you have learned from this very wonderful example, and you can even get the correlation coefficient, and we know the correlation coefficient can also be calculated by Rxy equals to, that is sine of beta 1, which is nothing but the square root of coefficient of determination. So you will have beta 1 square root of r square, and here the beta 1 is nothing but the slope of the estimated regression equation, which is y hat equals to beta naught plus beta 1 x. So this is the sample correlation coefficient, and if you start putting the numbers and compute it, you will get Rx equals to root of 0.8772, which is nothing but 0.73, in fact, which is nothing but Rx equals to 0.9366. That is a wonderful equation in that sense. Let us look at the assessing the fit. When I say the fit, it is about matching the relationship. So r square is nothing but the proportion of the variance in y explained by x. So the proportion of dependent variable explained by the independent variable. And RMSE is a typical prediction error, and whereas the plot gives you that scatter line and residual plot as well. And there are a variety of reasons why in hospital administration we use regression analysis, like clinical interpretation. You can translate the slope into clinical units. For example, we have the mmHg per year. And you can also have, let us look at the report of CI and p-value for the coefficient and try to avoid overstating the causation, the cause and effect relationship, although you're going to get in regression. So, but what is multiple regression analysis? The concept is quite clear. Several predictors, that means you will have several x's that will predict your dependent variable, which is nothing but y simultaneously. Now the equation remains the same except that we have several predictors. So y equals to a plus beta 1 x1 plus beta 2 x2, and it goes on till beta k xk and plus the error term. So there are multiple predictors in this. So you will also try to adjust each of these effects for the confounding variable, that is to control the measures. So one of the examples of the multiple regression analysis is the blood pressure or BP, which is approximation for age plus BMI plus sodium. So the slope here is B age, BP changes, and then per 1 year there is an increase and the holding is fixed. This is for the multiple regression analysis if you look at it. So we have age plus BMI plus sodium are the multiple predictors, and the slope for each of them you're going to calculate the slope which is beta naught or B BMI, BP change for 1 BMI unit, it gets increased. And same is the case with B sodium, which is nothing but BP changes for 1 gram per day sodium also gets increased. So this is the equation for the multiple regression analysis. you can clearly see from the partial effects. And then look at the case study also, like the length of the day or stays, how many number of days that the patient actually stays is dependent on the patient's age, which is a predictor. X here equals to age, surgery type, comorbidities, and other complications. So we have multiple independent variables. Did you see that? And we are trying to predict the length of the stay of the patient in terms of the days. So we use the prediction for the best, better bed management. So in a hospital, if you have too many beds, you can even you can predict that when is the patient going to get discharged using the regression analysis or multiple regression analysis. You can also solve it, and we have given you a small problem here. Look at the data. Here the small n equals to n, and age is given between 35 and 70. BMI is also given 22 and 33 and so on. And then the blood pressure is also mentioned. So the fit BP equals to 62 plus 0.9 age plus 1.2 BMI, that is for your illustrative purpose. So the interpretation is that for each plus 10 years approximately gives you 9 or plus 9 mmHg, and each 5 BMI approximately is nothing but plus 6 mmHg. So this makes it more clearer. What about the performance measures? The performance measure, you will get a lot of them. One is the accuracy. You can develop good accuracy. You can develop sensitivity, and you will also achieve specificity. And you can even have the calibration, that is predicted versus the observed risk. The minimization of this risk will actually give you a better prediction. Although regression analysis is being used in lots of areas, but there are few pitfalls. Some of the pitfalls, if you look at it, do not use regression analysis just to claim the causation. There will be repercussions for it if you use it. The other one, watch for other variables or control variables which would also have a lot of impact into it. That's why we call them the confounding variables and their interaction with the other variables. Now let us look at and check the assumptions before you pick up the interpretation. If your assumptions are quite clear, and then you will be able to take care of the prediction as well, or the interpretation and inferences. So overall, if you look at the model here, look at the plot y versus plot x and the fit line, and check the residuals, and you can easily illustrate glucose that is given in the predictor or the dependent variable. Then you have the age, which is x, and predict y for new x, that is always being represented. You can also get this residual plot as well. You can clearly see this in the image. So the residual randomly scattered gives you the OK patterns or the funnels, which also gives rise to the consider the transform or the new model. And then all the outliers, as we say, requires clinical review. So finally, you're going to make a decision out of the regression analysis. So what is that? That is the clinical decision support. So convert the prediction into risk category. You can have lower risk, moderate risk, and high risk. You can even categorize them into different other categories. And this, decision thresholds can actually going to help the clinicians to take a call and make a decision. And also over a period of time, you will be in a position to monitor them. And Of course, you need to follow the ethics and fairness and transparency in using these models. So what are these ethics and fairness? First and the foremost thing, try to avoid as far as possible any kind of biases against subgroups. And then audit with subgroups and then check the performance metrics. The other one, be transparent about the data and its limitations. And that's very important. You can even create a checklist like data quality checks, validation of the new patients, and the governance and monitoring plans. This is another example to get you through. So overall, if you look at it, we have been able to work the problems y equals to BP, x equals to age, BMI, fit model and interpretation. So BP is dependent on the age as well as the BMI, and that is why it's important to visualize all these areas. So far what we have learned, let us wrap it up or sum it up. So far we have learned about regression analysis. So regression helps us in predicting the outcomes and quantifies its effects. And the other one is also to check the assumptions. There are a bunch of assumptions like normality and others we have discussed, and then we have to also interpret clinically. And then as far as possible, you should be able to prefer simple, validated and transparent model to have better effects. With that, we come to the end of this regression analysis. I hope that you had a good time. We will see you very soon with yet another scintillating episode of statistics. Until then, it's goodbye from all of us.